Hello, I'm privileged to present to you the double technology that is the only technology today available that can help you save over 50% of the structural mass of the parts that you're working on. For that purpose, we have just made a few parts to give you a sketch of what is possible. And I'll begin with this part, which is the winglet of our aircraft. And this was originally a legacy quad laminate made part, and this structure, which is the top skin of this winglet, has been made by us in DD, and it has saved us about 30% of the structural mass. And let's say that this is the root of the winglet and this is the tip of the winglet. This is the leading edge, trailing edge. The entire area over here has, and the entire area over here in both the chord-wise as well as the span-wise axis has tapers. And these tapers in this thin material are extremely difficult to get unless and until you use DD, because DD by design, the laminate family itself by design is symmetric, in plane and out of plane, and that is the key over here. As you can see that we have 139 grams of this winglet, and this has been made out of a mold which I'll show you. This is the mold from which it has been made, and you see this sitting inside the mold without any issues, without any problems. This has been taken out. This has been cured at about 120 degrees centigrade, which is a high temperature. So this shows you that there is absolutely no change in the shape due to thermal cure of the part. There is no spring back, and the part is just fabulous. The other part that I will show you was initially a part like this. This is the vertical stabilizer's main rib, and this is made up of glass, weighs around 417 grams, and it's a fairly complex part because it has sharp corners and it is made from a single layer of material. Now this part is glass because in the vertical stabilizer we have antennas, so we cannot use carbon. But what we have done is we have tried to mold a vertical stabilizer rib out of carbon and out of DD carbon to show you what would be a part as complex as this, like when you mold it out of DD. So this is very strong compared to that part. First, and the reason is that we have put layers over here just to demonstrate the features of DD. And as you can see that if you make a cross section across this, you would see that this section is going to be thicker over here and thinner on the edges and thinner in the middle over here, just to show you that that this would create a very stiff structure across this section like that, and as well as along this axis. Now to show you that here, this is the axis along which this has been built, and this is our 0 degree axis. Then we have plus 50 and minus 50 DD angles over here, and this part is weighs around 330 grams, which is even though being twice as strong as that part, it has still got a weight advantage. So this is the advantage that you can get out of using DD on complex structure, and be able to mold a complex structure like this without any issues because of the way in which DD is made. The third part I will show you is actually this part. As you see, this is the original part, and we have made this part out of DD as well. And as you see, this is a pretty complicated part. It has inserts inside it, foam inserts over here, and metallic inserts over here, here, and here. And it has micro sandwich core over here, and it has a semi micro sandwich core over here, and it also has hard point strengtheners across the hard point itself. So this is a fairly complex structure, and this would be a very characteristic structure of all the parts that are there in our aircraft. And this part, as it is, weighs 2,919 grams of mass, and this is has got carbon, which is from Shomarat. This is unidirectional carbon to take care of bending stresses, as well as the fact that it has glass in various angles over here, and the axis over here for glass is varying all across the structure length, which makes it very difficult, to calculate it, second to build it. So I will show you how this comes out to be in out of DD. And this is the DD material, and as you can see, the hard points are there. The core, the micro sandwich core is over here, as well as over here and here, and all the hard points, allodyne hard points, including those which are stability points. These are all in over here, and this has only a single axis layup, and single axis layup helps us in taking a piece of cloth, a single piece of cloth from the of carbon, and molding this entire thing out of that single piece of cloth. The mass of this is 1,682 grams, and this is our landing gears tunnel. And what I wanted to share is that with these structures, we with a structure as complicated as that tunnel, it requires hand touch labor, and it requires somebody to do it by hand. And the reason is that any type of ATL or AFP machine, in order to lay up a structure like this, will not work, because there are attached hard points, there are discontinuities in the layup, because they are embedded structures inside the part, and also the part has very tight radiuses, and so on and so forth. So it requires being made out of by hand, and that's where DD not only does it excel in enabling a structure that has taper in it. So I will use the glass structure to explain to you what has happened, what we have done over here. Now, in that carbon structure, you cannot see that on that, but on this I can explain it to you. That is, from that end to this end, there is a taper in that, as well as there is a taper across this section over here, because this is in compression and tension and shear as well coming over here, because there is shear coming being transferred from these hard points onto this surface, and there is a taper across this. There is a taper across this which changes, and there is a taper across this. Now all these tapers are very easy to do on using DD, whereas they are a menace to do on a structure like this. And that is the reason why we have used that structure. Now let me go very quickly through A couple of advantages of DD, and one of those advantages is that if you have a structure that you have optimized to have a layup of 0 and 50 degrees, or plus minus 0 and plus minus 50 degrees, you don't need to store an enormous array of materials in your facility. You would need to have only that material, because you can just cut out all the materials from that, all the parts that you need to do along the axis, along a single axis on your cutting table, and you can place them whichever way you want. You don't have to stick to different angles or things like that. So it is very easy to and very material saving in order to cut materials that way. So you save the warehousing of various different types of materials, and you save on the wastage of cut material. So both those things are impossible to do with any other technology other than DD, because DD is a single axis layup. All the layup direction is just single. So this is, you could always make DD out of ATL or AFP, but the speed at which you would have an already knitted material like that of the non-crimp fabric from Shomarat, that C-ply, if you use that, you would be able to put a complete layup in one shot on your material of a size that you have just seen, without any issues. That kind of a thing, and that's rapid production technique, is not available with any other technology. So these are some of the salient things I wanted to share with you and show you the complexity of the layup that we have done to demonstrate the applicability of DD, as well as the fact that thermal cure plays an insignificant role in molding your parts out of DD. The last bit that I would like to share with you is that we did tapered coupons, and tapered coupons were done using Professor Tsai's patented card sliding technique, in which the layers are the same width and they are set at a slight distance from each other, which creates for a taper. Those panels were tested by NIAR, which is a FAA funded lab in Wichita State University for fatigue, and they took 500,000 cycles at 5 hertz at limit load. Each cycle was at limit load, and at the end of 500,000 cycles, a residual strength test was done to break the part. And believe it or not, after 500,000 cycles at limit load at 5 hertz, the residual strength of the material was equivalent to a pristine unloaded material. So that is the strength with which, that is the quality that you can bring to bear on your parts if you use DD. And we welcome you to look at all the material that is available, and to look at our at the exhibit desk. You will find several doctorate papers that have come out as a result of doctorate work. There are papers which have been submitted to conferences, and the most recent paper by Professor Tsai is in AIAA journal, that is also available. And there is a book that you can request from our team, and we'll be very happy to share with you this book that has B-basis data on the DD properties from the material that Shomarat makes. And the last bit would be that if you have any interest in DD, we'll be very happy to show you how to optimize your structure using a tool that has been developed with the research team of Professor Tsai, and that tool is called LAM Search, which will make it elementary for you to take your existing designs and get a DD that is specifically suited for your application, and in which you can put 98 load cases in one shot and get a optimized DD result out of that. So thank you very much for your interest and visiting our stand. Thank you.